Hello everyone. Today we will study about thermochemistry part 3 in which we will continue with some practice questions. So let's start. Disclaimer slide which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. So this is our index slides. So we will discuss today some practice questions from question number 30 to question number 37. Let's start by question number 30. The heat of combustion of carbon to CO2 is minus 393.5 kilojoule per mole. The heat released upon formation of 35.2 gram of CO2 from carbon and oxygen gas is. So options are 315 kilojoule, minus 31.5 kilojoule, minus 315 kilojoule, or 31.5 kilojoule. So you have 10 seconds to solve this question. After that, we will see the answer. Okay. So the correct answer is option C. That is minus 315 kilojoules. So let's see how it will be. So this is the reaction. Sorry. It should not be here. Yeah. So this is the reaction for the combustion of carbon to CO2. And the enthalpy for this reaction is given by minus 393.5 kilojoule per mole. And since heat released during the formation of 44 gram of CO2 is this, which is given, and 44 gram is the mass of CO2, right? So heat released during the formation of 1 gram of CO2 will be this given heat divided by the gram, that is 44 gram, right? So heat released during the formation of this amount of CO2 which is asked in the questions. So heat released during the formation of 35.2 gram of CO2 will be minus 393.5 multiplied by 35.2 divided by 44. And we have our the heat released, which is minus 315 kilojoule. Hence, option C is the correct answer. Okay, let's move to question number 31. Which of the reactions defines enthalpy, standard enthalpy of formation? Okay, so we have to choose from these 4 options. So options are C in the diamond form plus O2 in the gaseous form will give you CO2 in the gaseous form. Half of H2 molecule plus half of F2 molecule will give you HF molecule. N2 plus 3 of H2 molecule will give you 2 molecules of NH3. Or carbon monoxide plus half of O2 molecule will give you CO2. So you have to choose that for which reactions we get the delta H0F, that is standard enthalpy of formation. So you have 10 seconds to solve this question. After that, we will see the answer. Okay, so let's see the answer. Answer is B option, which is this reaction, the formation of HF molecule. So let's see how. So the delta H0F, that is standard enthalpy of formation, is amount of heat evolved or absorbed when 1 gram mole of a substance is formed from its constituent elements. Okay, remember constituent elements. For the formation of a compound, the constituent must be in elemental form. Therefore, formation of HF represents the standard heat of formation of HF. In the reaction, you can see that the if you see here that half molecule of H2, which is you can say H atom, or half molecule of F2, you can say F atom, gives you the HF molecule, which is also 1 mole. So even though the definition of standard heat of formation is also the amount of heat which is evolved or absorbed when 1 gram mole, okay, so 1 mole of a substance is formed, which is forming in the B option, from its constituent elements, or constituent element must also be in elemental form, which is the case in B option, right? Hence, B option is the correct answer. Let's move to next question, question number 32. The enthalpy of combustion of H2, cyclohexene and cyclohexane are minus 241, minus 3800 and minus 3920 kilojoule per mole respectively. Heat of hydrogenation of cyclohexene is. So we have to find the heat of hydrogenation of cyclohexene, right? So we have given the enthalpy of combustion for H2, cyclohexene and cyclohexane. Both are different. Okay, so options are 121 kilojoule per mole, minus 121 kilojoule per mole, 242 kilojoule per mole, or minus 242 kilojoule per mole. So you have 10 seconds to solve this question. After that, we will see the answer. Okay, so the correct answer is option B, that is minus 121 kilojoule. So let's see how. So the H2O formation, or you can say the combustion of H2 molecule is given by this reaction. So H2 react with half molecule of O2 will give you H2, right? And del H for this reaction is given as minus 241. And for the cyclohexene, which is C6H10, it is given the enthalpy of combustion as minus 3800. So this is the enthalpy for this reaction, which is cyclohexene plus 17 by 2 of O2 molecule will give you 6 molecule of CO2 and 5 molecule of H2. Next is for cyclohexane. Cyclohexane on combustion reaction with the 9 molecule of O2 give you 6 CO2 and 6 H2. And the enthalpy of combustion is given in the question as 3920 for this reaction, right? So we want to find out the heat of hydrogenation of cyclohexene, that is C6H10 plus H2 will give you C6H2. So we have to find out the enthalpy for this reaction. So on arranging these three reactions in a way that if we add equation first and equation second, and then the resulting equation will be subtracted from equation third, or the equation third will be subtracted from the resulting equation. We have to subtract or add the enthalpy for these reaction also in the same manner, right? So the final enthalpy for this reaction will be equation first enthalpy, which is minus 241 kilojoule per mole, and plus equation second enthalpy, which is minus 3800 kilojoule per mole. So plus minus will become minus, and minus equation third enthalpy, which is minus 3920. So bracket mein in the bracket, because it is in negative sign, right? So minus 3920 and minus minus will become plus, and we have to add these two and then subtract from these. So the answer, that is final enthalpy of hydrogenation of cyclohexene, is coming out as minus 121 kilojoule per mole. Hence option B is the correct answer. Okay. So let's move to next question. Question number 33. The enthalpy changes for the following processes are listed below. So we have some processes here and their enthalpy are also mentioned. So in the first process, Cl2 gas in the gaseous form going to become or form 2 atoms of Cl in the gaseous form. Enthalpy is given as 242.3 kilojoule per mole for this process. Next is I2 molecule in the gaseous form will give you 2 atoms of I in the gaseous form. Enthalpy of this reaction is given as 151 kilojoule per mole. In third, the ICl molecule will give you I in the gaseous form and Cl in the gaseous form. And the enthalpy for this process is 211.3 kilojoule per mole, right? In the last process, we have I2 molecule in the solid form becoming I2 molecule in the gaseous form. And the enthalpy for this process is 62.76 kilojoule per mole. Now, given that the standard states for iodine and chlorine are I2 and Cl2, the standard enthalpy of formation of ICl is. So, we have the standard state for iodine and chlorine, which is in iodine in solid form and Cl2 in gaseous form. And we have to find out the standard enthalpy of formation for the ICl molecule, which is in gaseous. So options are minus 14.6 kilojoule per mole, minus 16.8 kilojoule per mole, plus 16.8 kilojoule per mole, or plus 244.8 kilojoule per mole. So you have 10 seconds to solve this question. After that, we will see what will be the answer. Okay, so the correct answer will be C option. So for the standard enthalpy of formation of ICl gaseous, we have to follow this reaction. That is, half of I2 molecule plus half of Cl2 molecule will give you ICl molecule in the gaseous state, right? And if we find out delta H for this reaction, it will be half of del H for solid to gas of I2 molecule plus half of del H dissociation, that is enthalpy of dissociation for Cl2 molecule, plus half of dissociation of I2 molecule, which is finally in gaseous state, and minus the enthalpy of product, that is ICl, right? And on putting the values which is given in the questions already for every process, we have the enthalpy of formation of ICl molecule is 16.73, which is approximate to 16.8 kilojoule per mole. Hence, option C is the correct answer. Okay, let's move to the next question. Question number 34. On burning 4 gram of iron to ferric oxide at constant pressure, the heat evolved is 29.28 kilojoule. The enthalpy of formation of ferric oxide is, we have given the atomic weight of iron atom, which is 56. Right? For iron element, we have atomic weight is 56, and we have given that 4 gram of iron is burning to become ferric oxide. Okay, at constant pressure, and the heat which is evolving is 29.28 kilojoule in this iron to ferric oxide process. So we have to find out the enthalpy of formation of ferric oxide. So options are 81.98 kilojoule per mole, minus 81.98 kilojoule per mole, plus 819.8 kilojoule per mole, or minus 819.8 kilojoule per mole. So you have 10 seconds to solve this question. After that, we will see the answer. Okay, so the correct answer will be D option, which is minus 819.8 kilojoule per mole. So let's see how. So we have this reaction for the conversion of iron or burning of iron to become ferric oxide. So 2 molecules of iron plus 3/2 molecules of O2 will give you Fe2O3 ferric oxide, which is 1 mole. So 2 mole of iron will give you 1 mole of Fe2O3, and 1 mole of iron will give you half mole of Fe2O3. So moles of iron, we can calculate that 4 gram, right? 4 gram is the given mass divided by atomic mass, which is 56. So it is 1 by 14 mole. So moles of Fe2O3 will be we recommend, or we we add this thing that 2 mole of iron will form 1 mole of ferric oxide. So 1 mole of iron will form half mole of ferric oxide. So mole of ferric oxide forming is half mole. So of Fe, right? So half mole of Fe means half of 1/14 mole, right? Which is 1/28 mole. So moles of ferric oxide formed is 1/28 mole. And heat release, we have given heat is evolving as 29.28 kilojoule. So we have given the heat release. So the enthalpy of formation of ferric oxide is given by heat released divided by the moles of ferric oxide which is forming. Okay, so it will be minus 29.28, which is the heat release, divided by the moles of Fe2O3 formed. So this is 1/28. So it is kilojoule per mole, right? So negative sign is coming because given energy is in positive, right? But we have to consider the negative sign for the enthalpy of formation of ferric oxide. Negative sign due to evaluation of heat, and it is coming out as, on solving this, we have minus 819.84 kilojoule per mole. Okay, so this is the enthalpy of formation for the ferric oxide molecule, right? So we are considering here the burning of iron, right? And we can also consider that the formation of Fe2O3. That's why we have taken the enthalpy of formation of Fe2O3 per mole for the Fe2O3 molecule as this. Okay, hence option D is the correct answer. Okay, so let's move to question number 35. A cooking gas cylinder is assumed to contain 11.2 kilogram isobutane. The combustion of isobutane is given by this reaction: isobutane reacting with 13/2 O2 molecule, giving 4 CO2 and 5 H2. And del H for this reaction is minus 2658 kilojoule. Now, if a family needs 15,000 kilojoule of energy per day for cooking, how long would the cylinder last? Okay, so assume that 30% of gas is wasted due to incomplete combustion. This is the assumption, and we have to keep in mind this assumption while solving the question. Okay, now options are 34 days, 30 days, 31 days, or 24 days. So you have 10 seconds to solve this question. After that, we will see the answer. Okay, so the correct answer will be D option, which is 24 days. Okay, so we have given this equation here, and according to this equation, 58 gram of isobutane provides the energy which is given 2658 kilojoule, right? So this much kilogram of isobutane will provide how much energy? So it will be calculated as 2658 multiplied by 11.2 into 10 to the power 3, because we have to take in kilogram to gram, divided by 58, which is molar mass, and it is coming out as 55,13,268.9 kilojoule. So the daily requirement of energy is 15,000 kilojoule, which is given in the question here, that the family needs 15,000 kilojoule of energy per day for cooking. So the daily requirement of energy is 15,000. So we have to get this 15,000 in what amount of day, right? So we have also given that assume the loss of energy as 30%. So the daily requirement heat is the only 70%. Okay, you can say that, or you can say that the totally energy which is used for work is only 70% of this energy, right? Because only this amount of isobutane is present in a cylinder, and 30% is wasting, so only 70% is being used, right? So the 70% of this energy is the thing which we have to use for the total energy used for work, and cylinder will last. So we have this amount of energy, and we have to calculate that per day how much amount, this much amount of energy per day, and how much at how many days or in how many days it will consume. So cylinder will last for about 24 days, which is coming out by taking this energy which is used for work and dividing it by 15,000, because a 1 day requirement is 15,000 and we have calculated the total energy required. So we divide them and it is coming out as 24. So up to 24 days a cylinder will work for this family mentioned in the question, right? Hence option D is the correct answer. Okay, so let's move to next question. Question number 36. If the heat of neutralization for a strong acid-base reaction is minus 57.1 kilojoule, what would be the heat released when 350 centimeter cubic of 0.20 molar of a diabasic strong acid is mixed with 650 centimeter cubic of 0.10 molar monoacidic base? So we have given volumes and molarity here. Options are 57.1 kilojoule, 3.71 kilojoule, minus 57.1 kilojoule, or 0.317 kilojoule. So you have 10 seconds to solve this question. After that, we will see the answer. Okay, so the correct answer is B option, which is 3.71 kilojoule. So we have given moles and molarity and volume in the question. So we apply this formula. So for the millimoles of diabasic strong acid, M into V, that is 0.20 into 350, right, which is coming out as 70 millimole. Therefore, amount of H plus ions in the acid, or you can say diabasic strong acid, will be twice of 70 millimolar. So it will be 140 millimole. And similarly, the amount of OH minus ions in monobasic strong base will be the M into V. So 0.10 into 650 into 1, because it is monobasic, which is coming out as 65 millimolar. And you can clearly see that OH minus is the limiting reactant here, consuming almost completely. Since 1 mole of OH minus produces 57.1 kilojoule heat as mentioned in the question, so 65 into 10 to the power minus 3 moles of OH minus ions will produce how much heat, which is 57.1 into 65 multiplied by 10 to the power minus 3. So millimole to mole, and it is coming out as 3.71 kilojoule of heat or energy. Okay, hence B option is the correct answer. Okay, let's move to the question number 37. Consider the reactions given below. On the basis of these reactions, find out which of the algebraic relationship given in the options A to D is correct. So we have to find which option is the correct on basis on these two reactions. So first reaction, C in gaseous state plus 4H in gaseous state give you CH4 in gaseous state, and the delta H for the reaction is X kilojoule per mole. Second reaction is graphite, carbon in the form of graphite going hydrogenation and forming CH4 molecule, and the enthalpy of the reaction is Y kilojoule per mole. So options are X equals to Y, X equals to 2Y, X is greater than Y, or X is less than Y. So you have 10 seconds to solve this question. After that, we will see the answer. Okay, so the correct answer will be C option. So same bonds are formed in the reaction first and second, if you see, but no bonds are broken in the reaction first. So in the first reaction, our reactants are in elemental form, so no bonds is breaking up, right? Whereas bonds in the reactant molecules are broken in the reaction second, but in reaction second, the bonds are breaking. Like in the 2H2, it will giving you CH4, so 2H2 will become 4H first, right? So as energy is absorbed when bonds are broken, right? Like in the carbon, which is in solid form, going to carbon in the gaseous form, and 2H2 becoming 4H, right? So energy is needed in the conversion of these two processes in second reaction. So energy released in the first reaction is greater than the reaction second. Hence, X will be greater than Y. Okay. So this is a same thing. X is greater than Y. This is one thing. Okay. Hence, option C, mentioning X is greater than Y, is the correct answer. Okay. Thank you.